let's begin. So it's my honor to introduce Dr. Zheng Wu today. And Dr. Zheng Wu is assistant professor in the Department of Atmospheric and Environmental Science at Stony, Albany. And Zheng received her bachelor degree in atmospheric science from Sun University. And then she went to University of Utah for her PhD, where she focused on Stratosphere and Troposphere coupling using dynamical models. After that, she worked as a postdoc at ETH Zurich using AI to study atmospheric predictability. And since joining SUNY Albany in 2023, Zheng has been studying global tensor connections and S2S predictability by combining dynamical analysis and physical-based and AI model. So I think please join me in welcoming Dr. Wu.
Thank you, Chen, for the introduction. Is this good? Okay, perfect. Hi, everyone. Thank you for inviting me here and giving a chance to introduce the research in our group here. So today I'm going to talk about exploring predictability from stratosphere troposphere coupling using a range of machine learning or AI models from relatively simple random forest model to complicated and complex large-scale atmospheric AI weather emulators. So since we talk about stratosphere troposphere coupling, so I first have a brief introduction about the stratospheric polar vortex and its variability and the extreme event related to that. So the video here shows the potential vorticity at 10 hectopascal, which is around 30 kilometers above the surface. And the high PV value is shown in pink here. So it represents the strong stratospheric polar vortex, which is a strong westerly wind band with counterclockwise rotation centered at the polar region in normal winters. And in some winters, you can see that the polar vortex will split into two smaller vortices. And for example, in 2018, in February, you see the pink value split into two halves. And when this happens, is called the breakdown of the polar vortex, and is the occurrence of the extreme stratospheric circulation event called sudden stratospheric warmings, or SSW. So accompanying with the breakdown of the vortex, the temperature in the stratosphere increases by tens of kelvins in just a few days. So that's why we call this event sudden warmings events. So what causes these sudden warmings? So it caused by the interaction between the planetary waves and the mean flow in the stratosphere. So the planetary waves are generated in the troposphere by the mountains and the thermolancy contrast. And as this wave generated, they propagate upward into the atmosphere. And as they propagate upward due to the conservation of energy and decrease of density, the amplitude of this wave get increased. And when they reach the stratosphere, their wave amplitude gets so big and they will break. And they dampen the momentum into the mean flow and decelerate the mean flow. And as this process going on, the mean flow will decelerate from normal westerly winds to easterly winds. And when this happens, is the occurrence of the sudden warming events. So the question here is, why do we care about this event, which is 30 kilometers above the surface? Well, it turns out previous study found out that SSWs can influence the surface weather from weeks to months after the occurrence of this event. For example, in some winters, you may see the news about the cold air outbreaks in Europe, in UK, and in the US. So you see extreme precipitation or snowfalls and extreme cold weather across the continents. And they related to these sudden warming events. So we look at, so the whole picture here is we have the planetary wave generate the troposphere and propagate upward to the stratosphere and break, and then decelerate the polar vortex. And after that, the stratospheric anomalies can propagate downward to the surface and influence the surface weather from weeks to months after that. So this is the whole pictures of the stratosphere troposphere coupling. And so here we show the figure here is from a study by Butler et al. In 2017. So it shows the northern annual mode index or NAM index as a function of time in the x-axis and pressure in the y-axis. So it shows the composite of the of SSW events. So it shows the NAM index 60 days before and after the onset of that. And we can see the stratosphere anomalies can propagate downward from the stratosphere to the troposphere to the surface, and from 2 weeks up to 2 months after the onset of this event. And we call this pattern a stripping paint pattern. So due to this, stratosphere is considered as an important source of predictability on subseasonal to seasonal timescales for surface weather. So here is another picture showing the influence of SSW. So here it shows the surface response after the SSW event. So first figure shows the mean sea level pressure anomalies after the SSW event, and you can see the typical land pattern, negative land pattern of lactic northern northern Atlantic oscillation pattern or annual patterns in the mean sea level pressure and surface. And you can see extremely warm temperature in western Greenland and in eastern Canada after this event, and anomalous cold weather in northern parts of the Europe and Asia, and also in the eastern part of the United States. And for precipitation, we can see strong anomalies, dry conditions over the Scandinavia region, and then wet conditions over western and the central part of Europe. So given this influence or the impact of SSW, so if we can predict these SSW events on subseasonal timescales better, then theoretically we can further improve the surface weather predictions on longer timescales. So the goal or the question of this our study is trying to extend the predictability of this SSW. And the current predictability of this event in state of art forecasting system is around 1 to 2 weeks. So our question is whether we can further extend the predictability and then such that we can improve the surface predictions on longer timescales. And then what is the sources of the predictability of this SSW event? And then what is the role of the stratosphere variability in predicting surface weather or extending the predictability of surface weather? And can we actually use the stratosphere signal to predict surface weather? So with all these questions, we try to use a different way to different from the conventional way to study this question. So we use AI and machine learning tools to help to investigate this question, and hopefully they can provide different perspectives to answer the predictability questions or the sources of predictability questions for the stratosphere troposphere coupling. So today's talk, I'm going to talk about 3 different components. So the first component is focused on upward coupling of SSW, and we use a time-specific AI model with relatively simple architectures to see whether we can further improve the predictions on longer lead time and what are the sources of the prediction. And then second, we talk about the downward coupling. So after these events happen or after there's some stratosphere anomalies, whether we can use these anomalies or the features in the stratosphere to predict surface temperature on subseasonal timescale. And finally, we look at the two-way coupling predicting and simulating in the complex large-scale AI weather emulator. So in the first 2 parts, we build our own model to address questions. And on the last part, we evaluate and analyze the coupling in the established or in the developed AI emulator like GraphCast. So now let's take a look at the first part is the upward coupling from the surface, and we want to use the upward coupling to predict SSW events. So the goal here is to predict whether a winter has an SSW event. So the data is the output from the coupled climate model CM2.1 from GFDL, and we totally had around 8,990 years simulation, which had more than 5,000 SSW events. So the reason we use this data set is because this SSW event in general in observation is it happened at around 2 out of 3 winters. So there are not many these events in reanalysis and observation. So in order to increase our sample size, we use model simulation to train the model. The predictors in this case, I first focus on the heat flux anomalies from 300 to 1 hectopascal. So instead of the entire meridional heat flux as input, I first perform principal component analysis of the heat flux, and I only use the first 7 PCs to as input to the machine learning model. And the 7 PCs explain around 91% of the total variance of the heat flux in the stratosphere. And this heat flux is represent the upward propagating wave activities. As we talk about in the upward dynamics a few slides back. And the output of this model is the probabilities of 2 categories. One is winter with an SSW event and winter without an SSW event. So this is a classification problem. So the model we use here is the long short-term memory, or LSTM. So the reason we use long short-term memory is because our predictors, the PCs here, we have a time series. So long short-term memory is a neural network that is good at extract temporal evolution from the input data. So we want to use extract this temporal evolution to predict the weather and winter we have an SSW event. So here I shows the architecture, simplified version of the architecture used in this study. So one different way of the traditional LSTM model is that we add a tension layer after the LSTM layer. So I will not go into too much detail of this tension layer, but this layer will output a variable called normalized importance weight alpha. And this alpha is trying to tell us which time step in the time series is most relevant for the most important for the final predictions in this case. So in other words, it tells us which time step contain the predicted power of predicted signal to predict or classify whether the following winter will have an SSW event. So here we first take a look at the prediction, the performance of this model. So here I show the 4 evaluation metrics, which is accuracy, precision, recall, and F1 score. So the higher of these scores, the better the model or the better the performance is. So here we show the performance for the training, validation, and test data set in different colors. And we can see in general, the model predicts very good, and the accuracy of all those metrics is around about 90%. So which means most of the time the model can make the prediction correctly or is able to classify these events. Oh, and I forgot to mention that since this is a prediction, so the heat flux is 60 days and 1 day before the onset of an SSW event. And for normal winter, we use continuous 60 days before the target winter day. And so that the input is a 60 days time series, and is the lead time is basically 1 day before the target day. So now the interesting part is, so since this model performs good, and now the question is which time step contains the predictive information for the final output. So here we show the normalized importance weight alpha I just mentioned. So the alpha is a time series from 60 days to 1 day before the time event. And the area, because this is a normalized weight, so area under the curve is 1. And the larger alpha, it means it contains more information of the machine learning model. Use the time step to make a prediction. And as we can see here, if we use 60 days to 1 day before the onset of the event or half day, so the model will use the final 7 days as input to the model. And which means these 7 days contain most of the information or the model consider is most important to make the prediction. And it consistent. Excuse me. I just talked too loud. So it contains and is consistent with what we know in dynamics. In dynamics, we know the increase of the wave pulses is around 1 week to 2 weeks before the onset of the event. So that's why the model consider the last 7 days is the most important to make the final prediction. And so this is consistent with what we know. But now the question is, although the last 7 days the model consider is most important, but it does not mean that the time step in the previous days or in earlier days are not important. So, because we want to test the source of predictability, or in other words, whether earlier time step, heat flux at earlier time step, whether also contain important information for the prediction. So to test this idea, we only use 60 days to 16 days before the onset of the event, and only use this 45 period as outlined by the green box here as input to make the prediction. So in this case, the lead time here is 15 days. And now we see the performance here. So again, instead of using the entire 60 days period, we only use 45 days and with 15 lead times to make the prediction. And as we can see here, the model grades a bit, and the accuracy is around 70%. And you can see a variation in different evaluation metrics. But 70% is not bad because the climatological predictions in this case is only around 58%. So it's still the model is better than the climatological forecast. And now we want to know which time step in this 45 period contain information to make the predictions. So again, we take a look at the normalized importance weight alpha here. So now you can see the alpha is only goes through from 60 days to 6 days from the onset of the event. And you can see, so different line here is different. I run this model with different combination of training and validation data set. And so that's, you can think about it as ensemble. And the black line is the mean of the ensemble. And now you can see alpha start to increase around 35 days before the onset of the event. And the increasing is less abrupt as we saw in the previous analysis. So this information indicates that the machine learning model, first of all, does see the time evolution in the heat flux, and they use this time evolution of heat flux to make the prediction. And then the heat flux at earlier time stage actually did contain some predictive power to the prediction of SSW events. So now I would like to quickly summarize the first part. So first of all, machine learning model can be used to predict SSW events with lead times of 2 weeks. And actually, we can even vary this lead time a little bit to see if we use even a longer lead time like 3 weeks or 4 weeks, whether it's able to make prediction. I'm not showing it here, but if we use a lead time of 3 weeks, we can still make predictions using heat flux. better than climatological forecasts. And models with attention layer can provide a different perspective to investigate the predictability of SSWs and identify forecast windows beyond weekly timescales. And using this framework, we can actually evaluate and verify the precursors for SSW with different variables mentioned by previous study. So I only show key first here, but I also test this idea using zonal mean zonal wind structure and using mean sea level pressure to see whether those variables mentioned in previous study actually contain predictive power for SSW and at which times that they contain predictive power. So the second part, I will talk about the downward coupling. So the downward coupling, we talk about whether we can use the stratospheric anomalies to make predictions for surface weather. And this work is done by a student in my group, by Alina Vendades. Alina is a fifth-year grad student and co-supervised by me and Andrew Land in Wisconsin. So, so what she did here in this study is try to predict winter to winter temperature anomalies in Northeast Europe, which is highlighted by the red box here. And the output is the probabilities of two categories. One is whether the temperature anomalies is positive or negative. So again, this is a classification problem. And in this case, the data she used is ERA5 reanalysis daily data from November to March and from 1959 to 2020. And she separated this data into training period and testing period. Training period is used to update the parameters of the machine learning. And the testing data is used to evaluate the final model performance. And in this study, we compared two different machine learning models. One is long short memory I just introduced, and the other is a relatively simple machine learning architecture. It's called random forest. And she used a different input of precursors to make the prediction. So she first used pre-calculated indexes, for example, like the 100 Pascal geopotential height anomalous average over North Atlantic, which is used to mimic NL index. And then she used the stratospheric polar vortex geometry matrix. So include the shape, which tells the geometry of the shape of the vortex. So it includes the ellipse, central latitude, longitude, rotation angle, area of the ellipse, and then the long to short axis ratio. So, and she also used the stratospheric polar vortex strength as input to the models.
Just a kind of naive question about this. So before satellite, how much do you really believe the stratospheric analysis, especially over region, which doesn't seem to have a whole lot of observations?
Yeah, this is a good question. So she used reanalysis data here. I think there's a study that compare different reanalysis data sets about the quality of the stratospheric data. I think EI5 did okay job in this case. Maybe it's one of the best model right now we can get. So, but this is the data we have right now. So, but we can try to verify this result with apply to different reanalysis data set to see whether we get similar result and whether the model really learned the physical relationship. And we also try to apply this to numerical model output to see again, but numerical output also have their own biases. But again, the idea just to see whether it's able to capture the relationship between the vortices and the tremendous temperature. And the second set of predictors is pieces of different variables. So I will not read out all these variables here, but the idea of using these two different data sets separately is because we want to test the idea whether the polar vortex geometry indexes contained enough info. This 1D matrix contained enough information. And the second data set is to test whether if we add more information, like the spatial information of the predictors, whether it can add more information or whether this contains more necessary information to improve the predictions of surface temperature. So that's the idea why we use two sets of different predictors with different complexities. And again, the lead time of these two data sets are both 14 days before the target winter date. So the lead time is 2 weeks here. So totally we have performed 4 different experiments. So we have 2 different models and 2 different input data sets. So one is LSTM with the matrix, 1D matrix, and then LSTM with the spatial, that the pieces that contains information of the spatial pattern, and the random forest with the 1D matrix, and the random forest with pieces with spatial patterns. So we have 4 models here. And now we look at the performance of these 4 models. So here we perform 100 times cross-validation runs, and then we look at the statistics here. So after we train the model, we apply the model to the test data set, which is not seen during the training process, and then to use to evaluate final performance of the model. And we consider all predictions and look at the accuracy when we consider all the predictions, which is shown by the dark blue color here. And then we also only look at predictions that is confident, which means the predictive probability is larger than 90th percentile of all the predictive probabilities. And we call that prediction is confident. And when we only look at the confident predictions, you can see the accuracy of the prediction actually increased a little bit in this case. So which means when the prediction is more confident, the accuracy is also higher, which is not a surprise. And now we compare the predictions of different models. So first we compare whether a simple model can make the prediction by using the same input features, which is the 1D matrix here. So we can see for the confident predictions, the random forest actually show high accuracy compared to the LSTM model. And this result suggests that a really simple model like random forest in this specific case of application actually can perform as good or even better than a complex LSTM model. And secondly, we look at if we use the random forest, but we use more predictors with more information, which is with spatial information. And in this case, we can see the overall accuracy is very similar to the one we see in the previous slide, this 1D matrix. And actually, the distribution is different when we use different models, but it's not that different from each other, especially in terms of accuracy. It's even a little bit worse than we use the 1D matrix in this case. So in this suggests that the 1D stratospheric polar vortex geometry contains enough information to make a prediction for surface weather. If we include more information in the predictors, it does not really improve the prediction. So this is again compare the same model, random forest, but with the 1D matrix and the pieces with spatial pattern. Again, we can see that 1D matrix already contain enough information for this specific application to make predictions for surface temperature. So take home for this part of the study is that, so usually we tend to believe that a more complicated machine learning model may perform better, or the predictors contain more information, or more spatial pattern may be better. But for this application, the stratospheric polar vortex index that basically tells us the geometries of the vortex is good enough or contains sufficient information to make the prediction. And then a very simple machine learning model like random forest also good enough in this case to make the prediction. So you see, it does not always need to create a complicated machine learning model to make a good prediction. So this is the message we want to convey here. So the final part of this study is to look at, so in the first two parts, we build our own model. And you can see it's a relatively simple machine learning model to make predictions. And now, since we have this large scale AI and emulator like Penguin weather, GraphCast, they're really complicated, and they are like our numerical or the general circulation model, except that they completely learn from data. So now we want to see whether this such a complicated model, they are able to capture well the dynamics of the coupling between stratosphere and troposphere. So here is a brief introduction of this AI model. I think we all heard a lot about this model, so I will not introduce them in details, but the key differences of this model is that they can generate the forecast like our physics-based or conventional numerical weather prediction model. But the differences is there's no physical equation handwriting or encoded in this model. So they completely learn from the historical analysis data and then make predictions. So this is a complete data-driven model. So here we show the performance of this model. So along with, as you may see, there are many of different models developed basically every month or every week. So along with the development of this model, and many studies try to evaluate performance of this model from different perspectives. For example, the workbench tool, they try to evaluate the performance of this model in weather timescale. And the chaos band, they try to evaluate this model on subseasonal to seasonal timescale. And they also have the extreme weather bench, which try to evaluate the performance of this model in predicting extreme events. Now the question here is, for our study, the question is, although the performance is good, as you can see, compare to even outperform the physics-based model on medium range timescale, but with especially on troposphere variable and surface variable. But the question is whether this model they can predict the stratosphere. They can predict the stratospheric variability well, and whether they are able to capture the dynamics of the stratosphere troposphere coupling. So to answer this question, we use GraphCast, which is developed by DeepMind. And the reason we use GraphCast is because it was one of the very few AI models that was trained on the 37 pressure level with 10 levels above 100 hectopascal and the top layer at 1 hectopascal. So which means this model is trained on the entire troposphere column or troposphere layer. And GraphCast was trained on ERI5 analysis from 1979 to 2017, and we aim to analyze 4 SSW events that occurred in 2018, 2022, because this is beyond the training period. So we train the GraphCast, or we run the GraphCast with the initial conditions from days before and after this SSW event using ERI5 analysis. And then each prediction we run auto-regressively 6-hour forecast up to 39 days into the future. So now we look at the performance of this model in predicting the stratospheric extreme warming events. So here what I show is the solar wind, and 10 Pascal and 16 knot U-1016, which is used to represent the strength of the polar vortex as a function of time in the x-axis. So the predictions are initialized 14 days before the onset of the event, indicated by the red dashed line here. And the different color represent different SSW events, and the solid line are the predictions by GraphCast, and the solid lines are ERI5 reanalysis data. If we focus on the ERI5 analysis first, the dashed line, the black line is the mean of the 4 events, and the red line here is the mean absolute error of the 4 events. Now, if you focus on the black dashed line, you can see ERI5 around 1 week before the onset of the event. U-1060 start to decelerate, and on the onset date, it reverses from westerlies to easterlies, and this is the onset of the SSW event. And now, if we look at the solid black line or the solid lines in this plot, it's a prediction by GraphCast. Now we see GraphCast failed to predict this event, and actually GraphCast cannot predict any of these events at all. So in this case, not even deceleration of the event. So GraphCast cannot simulate the breakdown of the polar vortex and SSWs. So now you may say, okay, because the lead time is 14 days, right? So even we state of the art physics-based S2S model, like ECMWF, with 14 days lead time, it still cannot simulate SSW event. But you can see, although ECMWF cannot predict SSW, it can capture deceleration of the polar vortex. Now, if we look at a short lead time, like 4 days before the onset of the event. And now you can see for GraphCast, still the model cannot predict any event, and not even the deceleration of the event with 4 days lead time. But for ECMWF, you can see you can predict all the events very nicely, and even the exact onset of the event. So now the problem is GraphCast failed to predict this event even with very short lead time. The question is, why is this case? So to address this question, we look at the upward coupling from because SSW are driven by wavy flow interaction. So now we evaluate the upward coupling or the wavy flow interaction predicted by GraphCast. So we look at the momentum budget or the transform or Riemann equation. So on the first, we look at the ERI5 each term of the equation in ERI5. So this is average 1 week before the onset of the event. Now for ERI5, we can see the first term on the right-hand side is the convergence of the Eliasson Plum flux or EP flux. So the negative value means the convergence of the weights, convergence of the weights, indicates the deceleration of the weight. And the second term is the residual circulation due to the breaking of the planetary waves, and it's trying to offset the convergence of this wave. And then the third term is the sum of these two. So you can see when SSW or before SSW starts, the sum of these two terms is negative here. So indicates that there should be a deceleration of the polar vortex. Now, if we calculate the actual U tendency term calculated by the solar wind on the top panel here, we do see the negative value and the magnitude is consistent with the sum of the two terms in the equation. So ERI5 satisfies the momentum budget. And now, if we look at the predictions by GraphCast, and again, the first term is the convergence of the EV thrust. And we can see GraphCast can simulate a relative similar magnitude of the convergence of the waves. But GraphCast cannot capture the right residual circulation here. And the result, the sum of these two terms is a strong negative value. And this strong negative value should correspond to a strong deceleration of the polar vortex. But in fact, if we calculate the tendency term using the actual solar wind predicted by GraphCast, we see there's no clear deceleration. So we can see these two figures does not match each other. So in this case, it indicates that GraphCast failed to satisfy the momentum budget. And that is the main reason why GraphCast cannot predict any sudden warming events, because it cannot capture the waving flow interaction and does not satisfy the momentum budget. So now we're talking about upward coupling, and then we talk about the downward coupling. So now we initialize GraphCast on the onset date of the event, and then we look at whether it's able to capture the downward coupling. So first, we show the standardized polar cap to potential high anomalies as a function of phase after ionization or after SSW events, and then as a function of pressure on the y-axis. And in ERI5, we can see the dripping pane pattern as we see before. And what about GraphCast? Now, if we look at the dripping pane pattern in GraphCast, we can see GraphCast predicts a weaker anomalies in the mid-stratosphere and 1 week after the onset of the event, and it fails to capture the persistent positive anomalies in the lower stratosphere, and it failed to capture the downward coupling in the troposphere at the surface after the onset of the event. So you can see this clear in the difference field. So in the difference between GraphCast and ERI5, we can see negative potential high anomalies across the column and after the onset of the event. And now it indicates that GraphCast cannot capture the downward coupling of SSW. And now if we look at the normal winter, we initialize the GraphCast of normal winters. Then we look at the coupling in normal winters. And we can see that the errors in the normal winter is much smaller. We can see the difference between GraphCast prediction and ERI5 is much smaller in normal winter than the differences after SSW, especially when the model fails to predict SSW. So this indicates that SSW, or the failure to predict SSW, can actually influence the predictions of the troposphere and the surface variable. So we further look at this, you look at the spatial map of the prediction. So we look at which three predictions at 500 MPa to potential high, and after SSW and compared to normal winter. So the first row is after SSW, second row is normal winter. And again, we can see ERI5 is the non-typical NAO pattern, and the graph has failed to predict this typical NAO pattern after SSW. And you can see these large errors here. And compared to graph paths initialized on normal winter, we can see the mean absolute error actually is twice as large in SSW events, after SSW events, than in normal winter. So when graph path failed to simulate SSW, it also have large errors in the troposphere. And the same in the surface prediction. Here we look at the mean sea level pressure prediction. And again, we can see the mean absolute error in graph path is twice as large after SSW than in normal winters. So it indicates that the failure to predict this event do have an influence on the prediction of the surface weather. So here is a quick summary. So again, in this study, we try to evaluate how good is this large-scale AI weather emulator in predicting the coupling between stratosphere and troposphere. And we found out that graph paths cannot simulate the stratospheric variability and the extreme event, and which leads to the main reason is because graph paths fail to represent the wave-mean flow interaction in the stratosphere. And the result of that is it leads to larger errors in the prediction on troposphere and on the surface after these events. So now I talk about these three components in the stratosphere troposphere coupling. So I think the main idea I want to try to say here is AI and machine learning, they offer us a new lens of tool to look at the dynamics of the coupling from a new perspective. Maybe these perspectives we cannot see or may not be able to see easily use conventional statistical analysis or dynamical model. So with this, thank you for listening, and I'm ready to take questions.
Thank you, James, for talk. Now we open for question. Feel free.
I have a simple question. So, what would you do to fix graph paths? Simple.
Nothing more. This is a very challenging question in terms of model development. So it turns out one big reason that graph paths cannot simulate stratosphere well is because this AI model, they usually make the prediction on the troposphere and the surface very well. So when they train a model, they use a loss function to minimize the errors, to minimize the errors. And in this case, they put a lot of weighting in minimize the errors in the troposphere and surface, and kind of ignoring the stratosphere. So that's one reason why they cannot simulate well. But you may think, okay, we can increase the weights in the stratosphere, then the problem will solve. But trickily is they found out that then when they increase the weight in the stratosphere, the troposphere for a reason become worse. So now they're trying to come up with like a balanced way to see whether they can overall have good circulation, but without downgrading or degrading the prediction on the troposphere. So it's challenging. That's why I said.
Yes, so related with Henry's question, the model does not have these internal physical consistencies. Therefore, the EP flux is not driving the zonal circulation. One way possibly is to add the zonally averaged wind as the target in the training. Therefore, whatever EP flux you have would come together with that local. Has this been placed as a strategy for this particular type of phenomenon?
And for now, not that I know, but this is a good direction. So I think this is one way called physics guys machine learning modeling. So it's trying to put this information or code this information in the loss function I just mentioned, and try to make the model to learn the relationship between the flux and the mean flow. So that is possible. Yeah.
Another quick question. In this graph cast picture, you have a quite sharp transition around the 75 millibar. So is this an artifact of the design of the model, or?
I think so, because the main reason is this abrupt change or transition is because when they use the loss function to minimize the error, so it's more like a linear loss rate in the troposphere, but in the stratosphere it's a jump. So as it go high up, basically it's an exponential decreasing of the loss function in the stratosphere. So when you go high up, actually you can think about basically is not trained on, it's not learned enough from the data, because the loss basically like zero in layer up high up. So that maybe is the one reason for the abrupt change here. The second reason is because the resolution is not high enough, because it's trained from reanalysis data. And I think reanalysis here only have 200, 150, and 100, and actually is coarser than the 5, vertical resolution model we have right now. So that may be another tricky way to simulate the tropopause region.
And then can I have a quick follow-up? Yeah, so are you able to run the graph cast yourself, or you just take the simulation from ECNWF?
So we run
Graph.
the model by ourselves. So
But are you then able to train the model by yourself?
training is not possible unless we have very powerful computing resources at university. But fine-tuning is possible. So fine-tuning is not like completely train the model from scratch. So it will take lesser time to do that. And if you have some GPU resources, is possible.
Yeah, I have a question about your earlier part, because you were the first part you said that you use the upward heat flux, and then you also mentioned that you tested other parameters. So did you find other like pressure and stuff to be as useful or not as useful?
Well, since the heat flux I'm using here is the entire column from 300 to 100 Pascal, but I do separate this into 2 different parts. So I only use 300 and to I think 70, which is the UTRS region, and then the other one is the mid to upper stratosphere. And I found out that actually in this case they perform similarly in terms of the prediction, but the alpha it looks quite different. The weighting looks quite different when you use these 2 components. So it seems like if I use the heat flux, I don't have a data here, but if I use the heat flux in the troposphere, I think that in general the curve try to increase slower it's not as steep as this one. But I use the stratosphere only in the mid and upper stratosphere. The increase it is a little bit steeper at the end. So this is what I found. But how physically related to this is you need a second thought. But my theory here is because this wave is generated from the troposphere and takes time to propagate, and only some portion of wave can actually reach the upper stratosphere. And actually those waves break first and decelerate the wind. And the wind deceleration actually is from upper stratosphere downward. So that's why when you try to more close to the onset date, actually it's more linked to those upper stratosphere signal.
Yeah, following up here, so you're training your model to predict SSWs. I think you're training with GFPL CM2.1. So is that the low top model?
It's a high top model.
High top model, okay. Yeah, thank you.
Any other question?
Yeah, if I understood it correctly, in the early part of your talk, you said you had a 7,000-year run or something like that, which you used then to train. But the question then is the accuracy of the underlying model. Is if that model is not accurate, then is the training inaccurate because of inaccuracy in the parent model?
That's a very good point. So the next step, I haven't done it yet, so I'm going to do next is I need to put this model and apply this model to the analysis data to see whether it's able to make also reasonably good predictions and whether the weighting shows similar patterns to verify whether this dynamical model first is accurate or similar to the analysis, and also to see whether the model, machine learning model itself can be generalized to different data set or all the data sets for the same questions.
Yeah, well, it would almost seem to me that you have to do that step first before you then train on the 7,000-year run.
Well, we do look at the statistics and also some patterns in the model before we train this use data to train it. So we found out that in this model we do have a similar frequency of SSW event as in reanalysis, and we also see there's a similar correlation coefficient between the heat flux and the SSW as in reanalysis, and we also see the downward impacts. But actually, the tricky part is downward impact is not as good as the upward coupling. But in terms of upward coupling, I think this model is, well, I would say is similar or is a good representation of like ERI5.
Thank you.
Similar, I've kind of lost track. What is the current state-of-the-art accuracy of our weather or subseasonal models, dynamical models for sudden stratospheric warming events? I mean, and because I assume the goal here is to beat that, because we already have models that are giving predictions of these warming events, and so I always think of that as a baseline. So I'm trying to understand what the baseline is here, and then you're. So do these models, they predict sudden stratospheric warming events, right?
Yes. So right now the state of the art, I do have it in my backup slide, I think. Let me, yeah, here. So this is the state of the art predictability of the SSW event. So different color here is different model, and this is different lead time. So well, you can see basically the black line here is the mean of all the model. So you can see basically when we are at lead time of 6 to 10 days before the event, so the accuracy of this model in general that can correctly predict the event is around 15% or even lower than 50%. So that is the state. So that's why we said the current state of the art model, the predictability of SSW is around 1 to 2 weeks. It's capped here basically. So in what I did is I try to use longer lead time, like subseasonal times, like 2 weeks or 3 weeks. Use a model in the first part I said, and well, I can predict the accuracy of this event as around 70%, but it's not comparing the same thing as this model. So yeah, so that's why I still need to do a comparison to see whether it's comparable to this model. But it's better than.
Any other question? Yeah, I think it's time to conclude our section, and thank you for attending, and thank you for the wonderful talk.